Young thought that these receptors corresponded to the painter's primary colours. Taken by Young's three-colour theory, Maxwell wanted to test it. He devised a way to mix the primary colours with mathematical precision. He then tested those mixtures on a wide range of people to see if they all perceived the same colour. And he did this with a deceptively simple tool.
So this looks old. What's this then?
This is Maxwell's original colour wheel, which we are very pleased to have in the laboratory.
So that's the original thing.
This
that's what he
is
made.
The original thing. That's it. It's slightly beaten up. It's been used a lot, and that's because Maxwell used this to test out the mixing of lights among all his friends when he was here in Trinity College. It is pretty antique, as you can see, but the idea is you put different amounts of the coloured papers here, and then when you rotate them, then they mix up. And this works because of the typical time that the eye can respond is a 20th of a second. And so if it goes faster, the eye will interpret this as a mixture of the colours.
And this is a motorised version, is it?
This is a motorised version of it, and we can actually demonstrate how the colour mixing works with this rather pretty demonstration here. We were going to mix red and blue. We'll rotate it rapidly, and then we will see which colour we produce.
Just like his childhood zoetrope, Maxwell's colour wheel would spin so fast it would trick the human eye.
So if you were going to bring up that light,
this one here?
That's right.
Instead of moving figures, he'd be mixing colours just as artists did, but with mathematical precision. When he mixed red and blue, he got the same colour artists did when they mixed paint.
And that's kind of magenta, purple.
Yes, it's a sort of a magenta colour.
If Young was right, and there were receptors in our eye that responded to the artist's primary colours, then perhaps mixing red, yellow and blue in equal measure would produce white. But it didn't. So Maxwell tried different combinations.
We can begin now to reveal green as well as blue here. And if we just do a little bit of fiddling around with these discs, we'll be able to get equal amounts of red, green and blue, and we can then see what colours we observe. Okay?
So it's white. I mean,
it's white.
It's the only colour you call that, white.
So this is a beautiful demonstration of the fact that the primary lights, and notice the word light, not pigments, the primary lights are red, blue and green. And you can create any colour of light by suitable mixture of different proportions of these. What happens in paintings, pigments absorb light, whereas this is emitting light. So the upshot of all of this was that Maxwell was able to produce a rather beautiful colour triangle diagram which could indicate how you would create any colour by mixing the three primary colours.
Maxwell's colour triangle allowed him to pick a specific colour and work out how much of each primary colour would be needed to reproduce it. This was made possible by his mathematical precision and systematic testing. Maxwell's work swept aside a sea of confusion. He vindicated Young's theory and demonstrated that we see colours in paint differently to the way we see colours in light. He established the primary colours for light as red, blue and green. He realised the receptors in our eyes were sensitive to those three, and that by mixing them we perceived a vast range of colours. A few years later, he provided a stunning display that he was right. In 1861, Maxwell was invited to the Royal Institution in London to give a lecture on colour vision. But he didn't want to just talk about the principles. He wanted to demonstrate them to his audience. What he did would astonish them. Maxwell took 3 photographs of the same object. Each photo had a different filter on it. One was red, one was green, and one was blue. That gave Maxwell 3 photographic plates that he can use to project an image with. When Maxwell projected the image from the red photograph onto the wall, he got a red picture. In an age when photography was black and white, this was interesting, but hardly revolutionary. But if you project all 3 images onto the wall at the exact same spot, something special happens. The audience were looking at the world's first colour photograph. They were stunned. Maxwell had chosen the perfect subject for his picture, a brightly coloured tartan ribbon. By layering red, green and blue images on top of each other, Maxwell established the possibility of creating colour photographs. 150 years later, we use this method daily, because this 3-colour principle is used in colour TV, computer screens, even mobile phones. The colours we see on our screens, however big or small, are created by carefully mixing the primary colours. Maxwell's work on colour provides the basis for our present understanding of colour vision. He even proposed an explanation for why some people were colourblind. He said the receptors in their eyes were faulty, and that this radically altered how they perceived colour. 3 weeks after his colour show, Maxwell was elected to the Royal Society for his work on Saturn's rings and on colour. He was now counted amongst the finest physicists in Britain, and he was 29. That friend's advice was simple. If Maxwell wanted to learn something about electricity, he needed to know Michael Faraday. Faraday was a self-taught scientist who was revolutionising our understanding of electricity and magnetism. Maxwell's relationship with him was one of the most fruitful in 19th century science. We'd known about electricity and magnetism since ancient times. Most people had experienced the power of electricity through terrifying lightning storms. And we'd used magnetism in ships' compasses for centuries. They were considered completely separate things for most of our history. But in the early 19th century, scientists like Faraday were beginning to see a mysterious connection between the two. Deep in the heart of the Royal Institution, Faraday conducted experiments to understand how they were linked. In one experiment, a copper wire carrying electricity somehow provoked a nearby compass to move. In another, Faraday tried to do the opposite. Use a magnet to generate electricity.
Which led him to invent the electric generator, of which this is an example, where you have a permanent magnet and a coil of wire.
So the wire is wrapped around this bit.
Wire's wrapped around the cylinder, and you push and pull the magnet in and out of the cylinder to generate an electric current.
I like the lights. What's the Christmas lights for then?
Well, that's to show the electricity is passing.
Oh, okay.
Faraday did not use light-emitting diodes.
I think he should have done. That was a great mistake.
And all electricity power stations throughout the world use this principle of generating electricity that Faraday discovered down here in 1831.
Faraday had generated electricity simply by moving a magnet through a coiled wire. A discovery that would forever be associated with his name. But he was left with perplexing questions. There was no physical contact between the electric wire and the magnetic needle that moved, nor between the moving magnet and the copper coil. They were affecting each other through seemingly thin air. But how could that be?
Now, what Faraday thought was happening was that there were lines of force coming out at the end of the magnet, which were then cutting the wire within the coil to move electricity around the coil.
The idea of mysterious lines coming out of the magnet to generate electricity may have seemed outlandish, but Faraday had a simple experiment that could prove their existence.
So he took a very powerful permanent magnet, placed some paper on it, sprinkled iron farthings over it to represent the lines of force.
It never fails to impress either.
Of the magnet, and you can see the sort of three-dimensional
So these are coming up here and swinging around, and then coming down into this stuff here.
And Faraday sort of made permanent examples of this and sent them around to all his mates in Europe to show that space has structure as a very strong argument for his field theory.
So Faraday thought there was an invisible force field at work here.
Literally a field. I mean, Faraday sort of brings the word field into science, and it's invisible, as you say. But so this is why this is just a representation. It shows the existence of those invisible lines.